So our discussion starts with the concept of single stage rocket. Now see, in case of rocket, obviously it is essential for the rocket to burn fuel. And whenever we discuss whether it is single stage rocket or whether it is multi-stage rocket, usually if nothing is mentioned in the problem, we assume that it is moving in gravity-free space. Means the rocket has gone so much far from the Earth's surface, the gravity is negligible there. Okay. So we'll take this as a rocket. Forgive my drawing, it's pretty bad. So just bear with it. So fuel is burnt. So for all rocket equation, remember that the relative velocity of the gas emitted by the exhaust is constant. It is given by UREL. And the rocket has to burn fuel. So it is burning fuel at the rate of dm dt. But remember that dm dt, this term is actually because the mass is reducing with respect to time as the fuel is burnt. So obviously there will be a negative sign because this dm dt is a negative quantity. So what we will do is that we will keep a gamma as dm dt. But remember that to make gamma positive, we have to put a negative sign because dm dt itself is negative. So we have put the negative sign to make gamma positive. Okay. So I hope that till here everything is understood. Now another concept you all know, which is Newton's second law, and you will see in my video that I keep on repeatedly saying this. So because it is so important, it is so frequently used and it is so important. So what is Newton's second law? It says that if there is a momentum change with respect to time, there will be force. You all know that, right? So now in case of rocket, how the momentum is changed? So the momentum is changed because the gas is emitted, right? That relative velocity, and that velocity is constant. So the velocity with which the gas is emitted by the rocket is constant. So velocity is not changing here. But what is changing is the mass because the rocket is burning mass. So for rocket, we can say that U relative into dm dt is the force. Why I did so, I'll repeat again. For Newton's second law, F equal to d dt of mv. But suppose if v is constant, then v comes out and this is your dm dt. So basically we are using this concept to apply this equation. So UREL is the relative velocity. So I think this U is little bit like, for again you have to forgive my drawing and my handwriting is pretty bad. So UREL. So this is the relative velocity which is constant multiplied with dm dt. But dm dt is a negative quantity, but the rocket is moving in the upward direction. That means you have to give a minus sign to make this quantity positive. Now this is the force that is acting on this rocket, and the rocket, let us assume at that instant, has got mass capital M. So the equation is capital M dv dt, rocket equation. This is the rocket equation, differential equation of rocket motion. This is the differential equation of rocket motion. And this is what kind of rocket? Any rocket, single stage, multi-stage, all stages will follow this differential equation. Without this differential equation, no rocket can move. But in certain situations, in certain critical problems, there may be an external force supporting or opposing this motion. Then if that external force is there in those problems, you have to count that external force also. Now let's try some problem. Okay. This is a single stage rocket. It has a initial mass m1. The gas is exhausted with velocity u, and the rate with which the velocity the mass is burnt is gamma given. Okay, m1, and the final mass of the rocket is m2. The fuel is released or burnt at the relative velocity small u, and the fuel is burnt at the rate of minus dm dt. Now what is the velocity attained by this rocket when the mass from m1 has reached to m2? You can pause the video and try on your own, and those of you who want to see the solution, please continue. Minus u the relative velocity into dm dt. This is the momentum change of the rocket with respect to time. This is equal to how much? This is equal to m dv dt, where m is the remaining mass and dv dt is the rate of change of its velocity with respect to time. Now cancel the dt and do the side change. So what we get? dv is equal to minus u dm by m. Now what is the initial velocity of this rocket? 0. What is the initial mass of the rocket? m1. What you have to find for this single stage rocket is that when the mass has become m2, what is its velocity? So we integrate from m1 to m2 and 0 to v, and we get v is equal to minus u ln m2 by m1. So we can change this ln m1 by m2. So this is the equation 1, where v is the velocity attained by a single stage rocket. We'll now go for two-stage rocket. What is a two-stage rocket? This is the kind of rocket that you have seen in case of SpaceX videos, right? Where a certain part first goes and the fuel, this will be obviously the bottom part, where the fuel is burnt of that part, and this mass is not necessary for the rocket to carry because it is just unnecessarily making the rocket heavy. So what the rocket system will do, that it will disengage this mass. It will get detached from this mass. So this mass will fall and the remaining rocket will keep on going, and that remaining part of the rocket will obviously have another fuel, and it is going to burn the fuel at the same rate. So that means the first stage and the second stage will obviously follow the rocket equation. But what is happening? The mass that the rocket is carrying is changing. And in case of stage 1 rocket, the mass was changing only because the fuel is burnt. But in case of 2-stage or 3-stage or multi-stage rocket, what happens? That the fuel chambers, after it is burnt, is released, thus reducing the overall mass of the system. Okay, so let us try this. So this is a 2-stage rocket. So this 2-stage rocket initially has how much mass? m1, and then it keeps on burning the fuel and reaches the mass capital M. The moment it reaches the mass capital M after burning the fuel, the rocket does what? It disengages the fuel tank which has mass small m. So the remaining part, which is the capital M minus small m, now starts the stage 2, and the stage 2 has the final mass m2. Okay, what we need to find out in this problem is the final velocity attained at the end of stage 2. That is what we are after. Okay, so let us try to calculate. So for stage 1 or stage 2, you know the equation. The equation is m dv dt is equal to minus u dm dt. Cancel the dt, dv is equal to minus u dm by m. Integrate this from m1 to capital M, and here 0 to v1. What is v1? It is the velocity at the end of stage 1. So v1 is how much? v1 is minus u ln capital M by m1. So this means u ln m1 by m. This is equation 1. So this is the velocity at the end of stage 2. Now for at the end of, this is the, what is equation 1? This is the velocity attained by the rocket at the end of stage 1. Now as soon as the mass capital M is reached after burning the fuel, the rocket system now releases the fuel tank which has mass small m. So how much mass the rocket will now have? Capital M minus small m. So for the stage 2, I'll use the yellow color. For stage 2, the equation is again m dv dt is equal to minus u dm dt. Cancel the dt, dv is equal to minus u dm by m. But now the integration, remember, for the stage 2, what is the initial velocity? It is the final velocity of stage 1, and that is equation 1. So your lower limit will be now from u ln capital M1 by m to V2, which is the stage 2 velocity. And stage 2 ends where? When the mass reaches that m2 value. So your lower limit will be now capital M minus small m, because this is where the stage 2 got activated. And what's the final mass of the stage 2? It is the m2. So what we got the equation? V2 minus u ln m1 by m ln m2 by capital M minus small m. This means the value is V2 is u. V2 is equal to how much? If I do the side change, u ln m1 by m plus u ln m minus m by m2. Because of the negative sign, the fraction will change. So I can use the property of log a plus log b is equal to log ab. So V2 is equal to u ln m1 by m into capital M minus small m by m2. So this is the velocity at the end of stage 2 for the two-stage rocket. Velocity do you think is the more? This is the velocity of stage 1 and this is the velocity of stage 2. Which one is higher in magnitude? To do that, I'll just cut this equation. 1 minute. So that we can compare this side by side. Let's now compare these two equations. See, both of them, this one, equation 1, has numerator m1, denominator m2. Here also you have m1 and you have m2. So the deciding factor is that whether the log, the multiplication is more or less. Now you can see m1 by m2 is multiplied with capital M minus small m by capital M. This means your numerator here, this capital M minus small m will be obviously less than capital M because it's a fraction. So the ln m1 by m2 is multiplied with a fraction in the second case. But in the first case, ln of m1 by m2 is multiplied with an integer 1. So the velocity, the final velocity in the case of stage 1 rocket and the final velocity in case of two-stage rocket, this value will be more. So single stage rocket attains higher velocity. So this is a very, very important and this is a very interesting problem from rocket equation. Now let us try another question. This is now from an MIT question, an MIT archive question, and it's really thought-provoking and it's up to JEE Advanced level. So this rocket is kept horizontal. So this has mass m0. The entire rocket has initial mass m0. Okay. Now it is burning the fuel at the rate gamma. Gamma is given by minus dm dt. Just you know how it is, right? Now half of this mass m0 is fuel. So what is the fuel mass? Fuel mass is m0 by 2. This is a single stage rocket, so there is no stages here. So m0 is a total mass, so the rocket body plus the fuel has mass m0 and m0 by 2 is the mass of the fuel included in that m0. Okay. So now the table on which this rocket is kept has friction and its coefficient of friction is mu. Okay. Relative velocity with which the fuel is burnt is given as u, small u. First, we have to find out what should be the minimum value of the fuel ejection, which is u, the minimum value of u for which this rocket starts moving. That's our first equation. So first one is that find the minimum value of u, small u, with which the fuel must burn such that the rocket starts moving on this rough horizontal table. And the second part is that you have to find out the maximum velocity the rocket can attain. Okay. So those of you who want to try this question on your own, you can pause the video here and try this and come back to the video. And those of you who want to see the solution, stay with me and enjoy it. So first case. Now see, because of the fuel burn, what will be the force that will act on that horizontal rocket? We all know that U into gamma. And if this force is greater than equal to limiting static friction, which is mu mg, then this rocket will move. So what is the minimum value of gas exhaust? It should be mu mg by gamma. So this means if the U relative with which the fuel is thrown out by the exhaust system is greater than equal to mu mg by gamma, that means its minimum value is equal to mu mg by gamma, the rocket will start moving. Now let's go for the maximum velocity. Now try to understand. The rocket is burning the fuel, the relative velocity is greater than this value or equal to mu mg by gamma. So the rocket starts moving. What do you think will be the condition for which the rocket keeps on moving? As long as there is fuel, the rocket will move. And as long as it moves with an unbalanced force, because the force provided by the exhaust, which is U gamma, is more than the friction mu mg, because the kinetic friction mu mg remains constant, means the m is varying, but the frictional value mu mg remains constant. So I'll repeat again, as long as the force exerted by the fuel exhausted, which is U gamma, is more than mu mg, the rocket keeps on moving along I cap. And as long as the rocket keeps on moving along positive x-axis, its velocity keeps on increasing. I hope you have got the idea. So what should be the condition of maximum velocity? The maximum velocity condition is that as long as there is fuel, the velocity will increase. That means the maximum velocity attains where? Where the fuel just gets over. That means when the mass of the rocket is m0 by 2, at that instant, because m0 by 2 mass is burnt, so the remaining that m0 by 2 mass is there. So when the fuel is completely burnt, that means when the mass of the rocket is m0 by 2, at that instant the rocket velocity will be the highest possible velocity. And after that there is no fuel, so friction will now act and it will stop this horizontal rocket. So I hope this idea is understood. So to get the maximum velocity equation, I'll form one equation. I'll just remove this. So what is the velocity along x-axis? It is u dm dt, but dm dt is decreasing, so there has to be a minus sign. And the friction is in the opposite direction, that means minus mu mg. And this is the unbalanced force acting on the rocket at any instant. So at that instant, let us assume the mass of the rocket is m. So m dv dt. So that mass which is remaining, small m mass, its velocity has increased by a magnitude dv in time dt. So please go through this differential equation. I am assuming you have understood it. dv is equal to minus u dm by dt multiplied with dt by m minus mu g dt, and the mm cancels out. So here dt and dt cancels out. So dv is equal to minus u dm by m minus mu g dt. Please check. Is this differential equation understood? Okay. Now we have to integrate it with proper limit. So what is the initial velocity? The initial velocity will be 0. what is the maximum velocity? Let us assume that maximum velocity is Vmax. This is what I want to find out. I don't know that Vmax, so my upper limit is Vmax. When the mass, when the velocity is 0, the mass of the rocket is how much? The rocket mass was m0, right? And when it has attained Vmax, what is the mass of the rocket? Is m0 by 2. And this has to be integrated from mu g. Time, mu g is constant, so it comes out of the integration. Now, lower limit is 0 and the upper limit, I don't know. That upper limit I need. So, I need that time limit when the mass has become m0 by 2. So, what is that time? Capital T. Let us try to find out. For this, in your equation, it is given that minus dm dt is gamma. So, dm is equal to minus gamma dt. Integrate it 0 to t and integrate this from m0 to m0 by 2. Understood the equation? So, when the time capital T, your mass has become m0 by 2. So, that's the limit. So, we get m0 by 2 minus m0 is equal to minus gamma t. So, this means the value of capital T is equal to m0 by 2 gamma. So, this means this capital T that you have at the upper limit of time, we know the value. What's the value? That value is m0 by 2 gamma. Now, you put the data. So, if I put the data, what I am going to get? Let us solve this equation. So, to solve this equation, again, I don't have space. So, what I am going to do, I'll just minimize this equation. Obviously, I can change the page, but I'm not doing that. Otherwise, for you to understand, it will be a little bit difficult. If everything stays on the same screen, it is a little bit, decipherable. It is a little bit understandable. So, Vmax is equal to minus u ln m0 by 2 m0. So, cancel out, it becomes half minus mu g m0 by 2 gamma. So, this becomes Vmax is equal to u ln 2 minus mu g m0 divided by 2 gamma. So, this is the maximum velocity attained by the rocket. Go through this equation. So, we discussed two very interesting problems and an important concept with respect to JEE Mains or JEE Advanced, the rocket equation. So, I hope you really liked it, and if you really liked the video, please don't forget to like and subscribe. Thank you for watching. I'll bring more such questions in the next video. Tata for the time being.